The Great Pyramid of Giza should be impossible to build. Ancient civilizations moved and shaped stones, weighing more than 70 tons, with a sophistication that still mystifies engineers today. By the end of this exploration, you will understand the hidden engineering that made our earliest monuments possible. We will uncover how stones were cut with seams thinner than a blade and transported across vast distances without wheels. What does our modern world overlook about the ingenuity of the past? More than 11,000 years ago, long before the pyramids pierced the sky, a different kind of wonder rose from the hills of southeastern Turkey. Göbekli Tepe stands as a profound mystery, a sprawling complex of stone rings built by hunter-gatherers who had not yet invented pottery or the wheel. They carved and erected colossal T-shaped pillars, some weighing 20 tons, each one a monument to a vision we can barely comprehend. This was the dawn of monumental construction, a time when humanity shifted from building simple shelters to orchestrating colossal stone assemblies. What could compel a society of nomadic people to settle and dedicate generations to such a staggering task? The answer lies in a powerful mix of spiritual yearning, social bonding, and a deep, perhaps sacred, connection to the heavens. Experts studying the site suggest these projects required more than just muscle. They demanded sophisticated planning and a level of social organization we never thought possible for that era. A shared purpose must have united hundreds of individuals, coordinating their labor with a precision that speaks to a complex, cohesive society. The first immense challenge was the stone itself. The limestone pillars were quarried from a nearby plateau, and the initial work of extracting these monolithic blocks without metal tools is a puzzle in itself. Imagine the process, using simple stone hammers and levers to fracture bedrock along natural seams, then maneuvering these multi-ton giants from the earth. This was the foundational leap, the moment our ancestors first mastered the art of moving mountains, one colossal stone at a time. These early builders were laying a groundwork that would echo across continents and millennia, a hidden knowledge of engineering and collaboration that would eventually enable the wonders of the ancient world. Their story is not just one of stones and pillars, but of the human spirit's capacity to achieve the impossible when united by a common goal. The precision of this stonework defies simple explanation. In Egypt, artisans carved granite, one of the hardest stones on earth, using tools that seem laughably inadequate by modern standards. Their primary implements were copper chisels and stone hammers, yet they produced blocks with joins so seamless that the gap between them is often thinner than a single coin. How was such a feat possible? The secret lies in a profound understanding of the stone itself. One ingenious method involved wooden wedges. Workers would identify natural fissures in the bedrock, then hammer in dry wooden wedges. These wedges were then soaked with water. As the wood expanded with tremendous, relentless force, it would split the rock along a clean, predetermined line. This was not brute force, it was applied physics. For the fine work for achieving those impossibly smooth, flat surfaces, they turned to abrasives, a slurry of wet sand which contains quartz harder than the copper of their tools, was used with a simple drill. By patiently sawing back and forth with a copper blade and this sandy paste, or by spinning a hollow drill, they could slowly, meticulously grind the granite to a perfect finish. This entire process was a masterclass in staged labor. It began with the rough shaping from the quarry, using heavy stone mauls to pound away excess material. Then came the fine finishing, a painstaking stage where sand and copper saws did the work that power tools do today. Finally, the builders displayed a remarkable efficiency, often incorporating a stone's natural shape into the final wall, minimizing the work required. This same principle is visible on the other side of the world, at Machu Picchu. There, massive stones were fitted together with such incredible accuracy that you cannot slip a piece of paper between them. This technique, known as ashlar masonry, created structures that could withstand earthquakes by allowing the stones to shift and then settle back into place, a silent testament to an advanced knowledge of stress and movement. The true wonder is not just the technique, but the human element. Think of the generations of skilled hands, the patience needed to grind a single block for months, the unspoken language of craftsmanship passed from master to apprentice. This standardized knowledge, maintained entirely through oral tradition and practical demonstration, enabled the creation of monuments built for eternity. Once these perfect stones were shaped, an even greater challenge awaited, moving them across impossible distances. The quarries themselves were giant open-air workshops where the first act of this monumental drama unfolded. In Aswan, Egypt, a single unfinished obelisk offers a silent lesson in ancient engineering. This colossal needle of granite, still clinging to the bedrock, shows precisely how workers carved deep, narrow trenches around a monolith using nothing more than stone balls made of dolomite. They would pound these balls repeatedly against the granite, gradually pulverizing the rock along a straight line. For particularly stubborn stone, they employed fire setting, building controlled fires against the rock face. Once the stone was superheated, they would douse it with water, causing the thermal shock to fracture it along predictable planes. This was a dance of elemental forces, harnessing fire and water to command the earth. But the work began long before the first hammer fell. Site selection was a science in itself. Ancient engineers acted as geological surveyors, reading the landscape for natural fault lines and seams that would make extraction easier. They sought out stone not just for its durability, but for its aesthetic quality, choosing fine-grained limestone or striking red granite for their most important projects. A key insight was location, as archaeologists note these quarries were almost always positioned near waterways. This was a strategic masterstroke, ensuring that the most difficult part of the journey, moving the block, could be accomplished by floating it downstream. Before extraction even started, they tested the integrity of the bedrock. Using lever points, they would apply pressure to a section of stone, listening for telltale cracks that might reveal hidden flaws. To reach the best stone, they created vast stepped extraction pits, descending into the earth in terraces. This allowed them to access deeper, more uniform layers of rock, and it also created a highly organized workspace. Nothing was wasted. The debris from the quarrying process, the fragments and smaller stones, were recycled for smaller constructions or used as ramping material, a testament to an ingrained efficiency. At the Giza Plateau quarries, the level of organization is breathtaking. Individual blocks were marked with symbols and numbers, like pieces in a giant, pre-assembled kit. This indicates a true production line, where each stone was destined for a specific place in a grand design. Ponder for a moment the logistics of directing hundreds of workers to extract a single 70-ton block. It required a symphony of coordinated labor, with teams assigned to different tasks, from the initial trenching to the final levering of the stone onto its transport sled. This meticulous sourcing strategy was all about foresight. By investing immense effort at the very beginning, at the quarry face, they minimized the challenges of later stages. A perfectly extracted block with clean edges was far easier to move and set into place than a rough, irregular one. This brilliant beginning, this hidden world of quarry engineering, sets the stage for the next, even more incredible feat, the journey of these stones across the land. Moving these stones from the quarry was only half the battle. The real test of ingenuity began when the colossal blocks had to travel across vast, unforgiving landscapes. Visualize a scene from ancient Mesopotamia, where teams of laborers are depicted in tomb paintings, straining to pull a massive stone statue on a heavy wooden sledge. Experimental archaeology has confirmed their secret, a pathway made slick with water or a slurry of clay, dramatically reducing friction and turning an impossible drag into a manageable pull. This was the first principle of ancient transport, mastering the interface between the sledge and the ground. For shorter distances or heavier loads, they turned to rollers, placing a series of logs beneath the sledge and creating a primitive but effective conveyor system. As the sledge moved forward, workers at the back would retrieve the rollers and run them to the front, a continuous, rhythmic process that inched the monolith along. The engineering grew even more sophisticated with the construction of temporary ramps and causeways. These were not simple piles of dirt, but carefully compacted earthworks designed to distribute the immense weight of the stone evenly, preventing a catastrophic collapse. In the Andes, the Inca took this to another level. Their roads, engineered with stepped inclines and sturdy retaining walls, were specifically designed to facilitate the movement of enormous blocks up steep mountain terrain, turning sheer cliffs into manageable staircases for stone. The entire operation was a lesson in applied physics. Planners had to calculate the coefficient of friction to determine exactly how many workers were needed to pull a given load. A 50-ton block on a lubricated track might require a team of 150 people, all pulling in perfect unison to a rhythmic chant that kept them synchronized. In later periods, beasts of burden like oxen were incorporated, multiplying the pulling power available. But perhaps the most brilliant solution was the use of waterways. During the annual flood season in Egypt, builders would load stones onto specially built gargantuan barges. The rising waters lifted these vessels, allowing them to float the stones right to the base of the construction site, a natural elevator powered by the river itself. This intermodal network, combining land and river routes, is stunningly illustrated by the blue stones of Stonehenge. These stones, each weighing several tons, were transported over 150 miles from the mountains of Wales. The journey almost certainly involved dragging them on sledges to a river, then floating them along the coast on rafts before a final land journey to the sacred site. This was more than a mere transport operation. It was a pilgrimage of stone, a journey that would have required immense communal effort and sophisticated mathematical planning to coordinate. Just consider the cultural exchange this fostered, as different groups along the route came together for a shared, monumental purpose. After such an epic journey, the final, most delicate challenge remained, lifting these multi-ton stones and positioning them with an accuracy that still defies belief. The final ascent was the ultimate test of ingenuity. After a stone's epic journey, the challenge of lifting it into place demanded more than just muscle. It required a deep, intuitive grasp of physics. Ancient engineers mastered the art of leverage, using simple machines to achieve what seems impossible. One of the most elegant examples is the shaduf, a counterbalanced lift used for centuries to raise water from rivers. This very same principle, transferring weight using a long lever and a counterweight, was adapted on a monumental scale. To raise an Egyptian obelisk, workers constructed a towering ramp of earth and brick. At its peak, they built a sand-filled chamber connected to the obelisk's base. By slowly draining the sand from a small opening, they lowered the base in a perfectly controlled descent, using the obelisk's own immense weight and the leverage of its pivot point to guide it upright. This was not a sudden drop, but a careful, incremental settling into place, a dance of mass and momentum managed with breathtaking precision. the mechanics break down into three brilliant subpoints. First was the strategic placement of the pivot point. By positioning the fulcrum at just the right spot along a stone or lever, engineers could maximize their mechanical advantage, allowing a small team to exert force capable of moving a many-ton block. Second, they used temporary supports, wooden cribbing and packed earth, to stabilize the load at every stage of the lift, preventing a catastrophic shift. Finally, they integrated human power through capstans, large winches that teams would walk in a circle to slowly wind a rope, multiplying their collective strength. We see this in the construction of Greek temples, where evidence points to sturdy wooden cranes employing compound pulleys, enabling small groups to hoist marble blocks high into the air. Even the mighty lintels of Stonehenge, those immense horizontal stones perched atop the great pillars, were likely raised using a combination of levers and earthen ramps. Workers would have tilted one end of a lintel upward, packing earth beneath it, then tilted the other, repeating the process until the stone was high enough to be nudged into its final slot. This was engineering born from generations of observation and refinement. Each success and each failure taught a lesson, leading to techniques that were passed down and perfected over centuries. There were no formal textbooks on statics or dynamics, only a profound, accumulated wisdom about balance, force, and the properties of materials. This intuitive understanding of the physical world allowed them to transform raw stone into soaring architecture. With the stones finally lifted and poised, the last act of this ancient drama could begin, the intricate process of locking everything permanently into place. The stones did not simply rest against one another, they embraced. In the high Andes, the Inca perfected an architectural language where each block spoke to its neighbor through intricate, interlocking forms. This is the art of dry stone joinery, a method that abandoned mortar entirely, relying instead on custom-carved protrusions and indentations that locked multi-ton stones together like a three-dimensional puzzle. The result was a structure with a unique flexibility, a built-in resilience to the violent tremors that shook their mountain world. The technique was a masterclass in distributed force, where seismic energy was dissipated across countless small joints instead of concentrating on a single, weak point. To achieve this, builders first had to visualize the final fit. Experts suggest they likely created small-scale mock-ups or pressed clay into gaps to create a mold, a tangible guide for the painstaking carving to come. Every single stone was then meticulously shaped by hand, its unique contours crafted to match only its intended partners in the wall. This process involved several brilliant subpoints. First, workers often beveled the edges of each block, creating a slight angle that prevented the delicate corners from chipping as the stone was maneuvered into its final, tight space. Second, they incorporated keystone-like shapes, not for true arches, but for creating stable, self-locking clusters within the larger wall. Finally, they harnessed gravity itself, designing the joints so that the immense weight of the upper stones would gradually settle the entire assembly into an even more secure and unshakable fit over time. The Fortress of Saxehuaman in Peru stands as a breathtaking case study. Its colossal zigzag walls are composed of stones so enormous and so perfectly fitted that, after centuries of earthquakes, you still cannot slip the edge of a credit card between them. Each block dances with its neighbors during a tremor, shifting and then settling back into its original position, a silent testament to an advanced, intuitive grasp of structural engineering. Consider the profound patience this required. The skill of an artisan spending weeks or months to hand-carve a single block to its custom specifications. This method was not just about durability, it was a triumph of logistics, drastically reducing the need for binding materials and creating structures that were, in essence, monolithic. As we stand in awe of these seamless stone assemblies, a final, crucial layer of their design comes into focus: the invisible lines of alignment and celestial orientation that guided the hands of their builders. The stones were locked into place, but their true purpose extended far beyond the earth. These monuments were not just built for the ground beneath them, they were meticulously calibrated to the heavens above. The Great Pyramid of Giza stands as a testament to this celestial obsession, its sides aligned to the 4 cardinal directions with an error of less than 1/15th of a single degree. This precision was achieved millennia before the magnetic compass, using only the sun and stars as a guide. Ancient engineers were not merely constructing tombs or temples, they were building gateways to the cosmos, embedding the rhythms of the universe into stone. Their methods were both elegantly simple and profoundly sophisticated. One primary tool was the gnomon, a simple vertical rod. By carefully tracking the length and direction of its shadow throughout the day, particularly at the moments of the solstices, they could establish a true north-south line with remarkable accuracy. In Egypt, a device known as a merk, it was used, a forked sighting tool that allowed priests to track the transits of specific stars across the night sky, effectively turning the horizon into a giant celestial clock and compass. This knowledge was then physically manifested in the architecture itself. The narrow air shafts inside the Great Pyramid, for instance, were not for ventilation, but were precisely angled to point directly at significant stars like Sirius and the circumpolar stars that never set, creating a permanent connection between the pharaoh's resting place and the eternal heavens. This celestial choreography is even more visible at a place like Stonehenge. The entire structure functions as a massive astronomical observatory, where the heel stone is positioned so that on the summer solstice, the rising sun appears to balance perfectly atop it when viewed from the center of the circle. Across the ocean at Chichen Itza, during the spring and autumn equinoxes, the setting sun casts a series of triangular shadows down the steps of the El Castillo Pyramid, creating the illusion of a feathered serpent slithering down to the earth. This effect was not a happy accident. It was the result of generations of accumulated astronomical data and painstaking architectural planning. The integration went beyond simple alignments. These builders frequently encoded sacred geometry into their designs, using ratios like the golden mean to create proportions that were not only pleasing to the eye, but were also believed to reflect the fundamental harmony of the cosmos. A stunning example of this intricate relationship between light and stone can be found at Fajada Butte in New Mexico. There, 3 large stone slabs are positioned in such a way that dagger-like shafts of sunlight fall upon spiral petroglyphs carved on the rock face behind them. These light daggers strike the center of the spirals only on the solstices and equinoxes, marking the changing seasons with a silent, predictable ceremony. This achievement required an interdisciplinary genius that blurred the lines between science, mathematics, and spiritual belief. The surveyors who laid out these sites had to possess a deep understanding of spherical astronomy to project celestial movements onto a flat landscape, and the mathematical skill to translate those angles into monumental construction. This celestial precision was the final, invisible layer of their engineering, a symbolic language written in alignment and proportion that connected the human world to the divine order of the universe. The line between engineering and ritual was often invisible. In Mesopotamia, the construction of a ziggurat was far more than a building project. It was a reenactment of cosmic creation itself. Each tier of the massive stepped pyramid represented a stage in the formation of the universe, built with specific rituals designed to infuse the very bricks with divine presence. The process was a sacred duty where every phase, from quarrying the first brick to setting the final capstone, was accompanied by ceremonies to ensure harmony between the human, natural, and supernatural worlds. This was symbolic engineering, where the physical form of a structure was a direct expression of a spiritual belief. Temples were meticulously oriented to reflect mythological narratives, such as aligning a gateway with the path of a sun god. Builders selected specific stone types not just for their durability, but for their believed spiritual power, choosing materials that resonated with the deity to be honored. Experts studying these sites note that the dimensions themselves were often dictated by sacred numbers, ratios considered perfect and divine. Before a single foundation stone was laid, priests would perform rituals and bury foundation deposits, artifacts or offerings meant to bless and protect the site for all eternity. A stunning case study of this principle is Angkor Wat in Cambodia. The entire temple complex is a vast stone model of Hindu cosmology. Its towering central peaks symbolize the mythical Mount Meru, the axis of the world, while the surrounding moats represent the cosmic oceans that were believed to encircle it. Every corridor and courtyard maps a spiritual geography, making the act of walking through the temple a symbolic journey through the universe. Ponder the immense motivation this provided. For the community, building such a structure was not backbreaking labor. It was a form of collective prayer, a direct participation in the divine order. The incredible engineering precision was likely driven by this deep desire to manifest an ideal, perfect form on Earth, a permanent home for the gods. This profound fusion of belief and technical skill extended even to the atmosphere within these spaces, to the intentional design of sound itself. The stones themselves could sing. Deep within the hypogeum of Malta, a subterranean labyrinth carved from solid rock, a single spoken word can transform into a resonant hum that seems to fill the very bones of the listener. This is not an accident of architecture, but a deliberate engineering of atmosphere. Researchers have found that specific chambers within these ancient spaces resonate at a frequency that can alter brainwave patterns, potentially guiding participants into profound states of consciousness during rituals. The ancient builders were not just masters of stone, but also architects of sound, using the principles of resonance to craft immersive spiritual experiences. They understood that sound was a physical force that could shape human emotion and unite a community in a shared, vibrational moment. This acoustic design required a deep, intuitive knowledge of how sound waves behave. At Newgrange in Ireland, the magnificent corbelled stone roof over the long passage tomb does more than just keep out the rain. Its precise curvature and the dimensions of the passage itself are tuned to amplify and carry certain frequencies, turning a chant or a rhythm into something otherworldly. This sophisticated sonic engineering breaks down into several brilliant techniques. Builders strategically placed niches and alcoves in walls to create complex echo patterns, causing sound to linger and fold back upon itself in a way that felt supernatural. They also carefully selected building materials for their sonic properties, knowing that dense limestone would reflect sound sharply, while a more granular sandstone would absorb it, creating pockets of silence. Perhaps most cleverly, they aligned entire chambers to capture natural soundscapes, positioning entranceways to funnel the sound of wind or trickling water into the heart of a sacred space, integrating the voice of the earth itself into their ceremonies. A stunning example of this intentionality is found at the Mayan pyramid of Chichen Itza. A single clap at the base of the massive El Castillo structure does not return as a simple echo, but as a piercing chirp that perfectly mimics the call of the revered Quetzal bird. This was likely interpreted as direct communication with the spirit world, a divine response engineered into the very steps of the pyramid. Consider the powerful unifying effect this would have had. During a collective ceremony, the shared experience of these extraordinary sounds, the feeling of the very air vibrating around them, would have dissolved individual boundaries and forged a powerful sense of communal identity. The acoustic environment became an invisible participant in the ritual, guiding emotion and reinforcing belief. To achieve such precise auditory effects, these early engineers must have relied on tools and techniques just as sophisticated as those used for celestial alignment or stone fitting, a hidden technology of tuning and measurement that we are only beginning to understand. The sophistication of these ancient sites stands in stark contrast to the apparent simplicity of the tools that created them. At Olmec sites in Mexico, workers carved colossal heads from solid basalt using implements made from even harder stones like jadate. They achieved this not through force but through a patient, grinding abrasion, a testament to the power of persistence over pure power. The toolkit of the early builder was a study in elegant efficiency, each item designed for a specific, vital role. For the heavy, rough work of quarrying, there were stone hammers, massive hand-held mauls used to pound and fracture bedrock. For finer work, like carving precise slots or channels, they turned to antler picks and copper chisels, tools that could be sharpened and resharpened to maintain a fine point. The true genius, however, lay in how these tools were combined. Workers would often use fire to superheat a section of rock, then quickly douse it with water, creating thermal shock that weakened the surface and made it easier to break away with their stone hammers. For cutting, a simple copper saw became a powerful tool when used with a slurry of wet sand. The quartz in the sand, being harder than the copper, did the actual cutting, allowing them to slice through granite with patient back and forth motion. We can categorize these tools by their core functions. First were the pounding tools, the heavy mauls and hammerstones used for the initial rough shaping. Next came the cutting and drilling tools like chisels, saws, and the bow drill, which spun an abrasive tip to bore holes or create intricate details. Finally, and just as importantly, were the measuring and layout tools. Builders used knotted cords for measuring distances, wooden squares and set squares for ensuring perfect right angles, and simple plumb bobs made from a string and a weight to verify that their walls were truly vertical. The introduction of metal tools during the Bronze Age certainly revolutionized this process, making quarrying faster and allowing for more detailed carvings. Yet, in a fascinating twist, many of the older, primitive methods persisted for centuries. Why abandon a technique that was perfectly reliable and required no scarce resources? The real innovation was not in constantly inventing new tools, but in maximizing the potential of the tools they already had. Today, archaeologists can read the story of this craftsmanship in the marks left on the stones themselves. A series of small, regular pits tells of patient pecking with a stone hammer. Long, straight grooves indicate the use of a saw with an abrasive slurry. These are the literal fingerprints of the ancient artisans, a permanent record of their skill and methodology. This entire system of tool use was not random. It was a physical application of a deeper, underlying intelligence, guided by precise mathematical principles that dictated every cut and every measurement. These silent blueprints were written in geometry. The Parthenon in Greece stands as a perfect expression of this, its dimensions meticulously governed by the golden ratio, a proportion so deeply pleasing to the human eye that it seems to echo a universal harmony. This was not an isolated phenomenon. From the slopes of the Great Pyramid, built using the precise Pythagorean triple of 3, 4, and 5, to the vast circular ditches of Neolithic henges laid out with ropes to ensure a perfect diameter, ancient architecture is a language of hidden mathematics. These builders were not just stacking stones, they were encoding cosmic order into physical form. Historians note they relied on standardized units of measure, like the Egyptian royal cubit, a length derived from the human arm that ensured every block in every corner of a massive project would fit together perfectly. This created a modular system where entire structures could be planned and built from a set of repeating, interchangeable dimensions. The tools for this were elegantly simple but required immense skill. A length of rope and 2 stakes became a giant compass for drawing perfect circles. A straight edge and a set square, tools we still use today, allowed them to project flawless right angles and straight lines across a landscape. This geometric thinking extended beyond the basic layout. In many cultures, we find fractal patterns where the same intricate, self-repeating shapes appear in the grand plan of a temple and again in the minute details of its carvings, creating a visual rhythm that connects the immense to the infinitesimal. A profound example is the design of Hindu temples, which are often based on a mandala, a complex geometric diagram representing the universe. Every single proportion, from the height of the central tower to the width of the doorways, is calculated to reflect spiritual principles and the hierarchy of the gods. How was this intricate knowledge maintained and taught across generations without written textbooks? It was a living tradition, passed from master to apprentice through hands-on practice and oral recitation. A young builder would not just learn to measure, but to feel the truth of a right angle, to understand the tension in a surveying rope that signaled a perfect circle. This mathematical foundation likely emerged from a blend of keen observational science and an intuitive sense of balance and form, a deep-seated human recognition of the patterns that underpin our world. The very stability of their monumental structures rests upon this invisible, geometric skeleton, a precision that set the stage for the next great leap, the evolution of the arch. The dome of the treasury of Atreus is a marvel of counterintuitive physics. Here, ancient builders created a soaring, beehive-shaped chamber, not with a true arch, but by stacking rings of stone, each one projecting slightly inward over the one below. This is the principle of corbelling, a brilliant technique that cantilevers weight outward, transferring the immense load of the ceiling down through the walls in a stable, continuous curve. To achieve this, every stone had to be carefully tapered, their inner faces angled to close the final gap at the apex with a single, perfect capstone. Engineers faced a constant battle with gravity, as each inward step created a powerful outward thrust. To counteract this, they often backed the entire structure with tons of earth and rubble, creating a stabilizing counterweight that locked the entire vault in place. This method allowed for the creation of vast, enclosed spaces using only locally available stone, a revolutionary step toward grand interior architecture. The ingenuity extended to other structural challenges. Above heavy doorways, builders would leave a small, triangular opening, a relieving triangle. This simple void acted as a pressure release, diverting the weight of the masonry above away from the vulnerable lintel stone below, preventing it from cracking under the strain. This same corbelling logic was adapted vertically in the Nurag of Sardinia. Massive stone towers where interior chambers and staircases were all spanned by these self-supporting, overlapping layers. Far across the world, the Maya perfected their own version in the palaces of Palenque. Their corbelled vaults used flat stones angled inward to create steep, triangular ceilings that allowed for taller, more majestic rooms, a testament to the method's global appeal. Consider the generations of trial and error behind this innovation. A single miscalculation in the angle or size of a stone could lead to a catastrophic chain reaction, a collapse that would have taken months of labor to rectify. This was engineering learned through direct, hands-on experience, a slow accumulation of wisdom about load and balance. These vaulted forms did more than just keep the rain out. They created protected, resonant spaces for sacred rites and royal functions. setting a foundational principle that would one day inspire the graceful arches and domes of later ages. Water was the silent guardian of these stone cities. At the sprawling complex of Angkor in Cambodia, engineers designed a masterpiece of hydraulic control, weaving canals and reservoirs into the very fabric of the monument. This was not an afterthought, but a foundational strategy to protect their colossal investment from the relentless tropical rains. The primary threat was erosion, the slow, insidious washing away of soil that could undermine the heaviest stone foundations. To counter this, they sculpted the land itself, grading vast platforms and plazas with a subtle, precise incline that channeled rainwater away from the structures and into a waiting network of drains. This brilliant water management extended beyond mere protection. They created immense artificial lakes known as barrays, which served a triple purpose. These reservoirs supplied water for the thousands of workers and residents, supported the agriculture that fed the population, and created stunning reflective pools that doubled the visual impact of the temple spires against the sky, while also cooling the surrounding air. The system's sophistication is breathtaking. Archaeologists have uncovered evidence of sluice gates and weirs, adjustable controls that allowed them to manage water levels with precision, directing flow where it was needed most. This same hydraulic genius is evident in the rock-cut city of Petra. There, Nabatean engineers carved intricate networks of terracotta pipes into the cliffs and chiseled vast cisterns from solid rock, capturing every precious drop of seasonal rainfall to sustain the city through long, arid periods. The principles break down into several key innovations. First was the strategic placement of aqueducts to direct natural springs into ceremonial pools, ensuring a constant source of pure water for rituals of purification. Second, the creation of subterranean drainage channels that ran beneath streets and plazas, carrying water efficiently away without disrupting the city above. Finally, the use of waterproof linings like packed clay or lime plaster to seal reservoirs and prevent precious water from seeping back into the earth. A stunning early example comes from Mohenjo-Daro in the Indus Valley, where great communal baths were built with sophisticated drainage and waterproofing, showcasing an urban planning philosophy that centered on water access and sanitation. Consider the foresight this required. By integrating these systems from the very beginning, builders dramatically extended the lifespan of their monuments, mitigating the environmental damage that would otherwise crumble lesser structures over centuries. This deep, localized understanding of hydrology, of reading a landscape's water flow and adapting to it, represents a different kind of engineering wisdom, one that worked in harmony with the forces of nature. This mastery over water hints at a broader, more fundamental skill, the ability to adapt these monumental principles to the most extreme and varied environments on Earth. Ancient temples in Greece were built to dance with the earth. Their column drums were not rigidly fixed, but rested on precise stone pivots, allowing the entire structure to sway and shift during a tremor before settling perfectly back into alignment. This was a profound understanding that to resist a force of nature, you must first learn to yield to it. Ancient engineers did not fight their environment. They designed in harmony with it, creating monuments with a built-in resilience that has allowed them to stand for thousands of years. One of the most ingenious techniques was the use of flexible foundations. In regions plagued by earthquakes, builders would often lay a deep bed of alternating sand and gravel beneath their stone footings. During a seismic event, these granular layers would move and compress, absorbing and dispersing the destructive energy before it could travel upward into the main structure, acting as a natural shock absorber. This principle of elasticity was woven directly into the walls themselves. In some cultures, like the ancient Inca, builders incorporated timber lacing, weaving long, flexible wooden beams horizontally through the stonework. These beams acted like the springs in a modern car, flexing under stress and then returning to their original shape, preventing the rigid stone from cracking apart. The design of the structures themselves reflected this deep-seated knowledge of physics. Many pyramids and towers were deliberately tapered, built wider at the base and narrower at the top. This simple shape dramatically lowered the center of gravity, making the entire edifice far more stable and resistant to toppling. Builders also employed strategic expansion joints, leaving deliberate, thin gaps between large sections of masonry. These gaps allowed different parts of a building to move independently during thermal expansion or ground settlement, preventing stress fractures from spiderwebbing across the entire facade. A stunning case study of this localized wisdom is Japan's Ishi-no Hoden, a massive floating stone shrine that has withstood countless tsunamis. Its unique, partially submerged design and its connection to the native bedrock allow the colossal stone to move with the tremendous force of the water, rather than rigidly opposing it. This reveals a long-term thinking that is almost incomprehensible today. These builders were not constructing for a decade or a century, but for millennia. They selected specific stone types not just for their beauty, but for their inherent flexibility, choosing materials that could bend and absorb impact rather than shatter. They observed how the local environment behaved at its most violent, and they engineered their creations to endure those specific challenges. This foresight required more than just technical skill. It demanded a cultural commitment to permanence, a collective will to build something that would outlast generations. That enduring legacy was only possible because of the vast, organized communities that brought these monumental visions to life. The sheer scale of labor at the Giza plateau is almost beyond modern comprehension. Thousands of individuals lived in purpose-built villages near the construction site, their lives a tapestry of coordinated effort. This was not a chaotic mob of workers, but a highly structured society engineered for a single, monumental purpose. The true wonder was not just the movement of stone, but the seamless orchestration of human potential. Tasks were meticulously divided into specialized teams, with some groups dedicated solely to quarrying, others to the logistics of transport, and a final cohort of master artisans responsible for the precise placement and finishing of each block. This division of labor was the bedrock of their efficiency, allowing each team to develop deep expertise in their specific craft. Historians examining the remains of these worker settlements have uncovered a surprising level of care. Administrative records and the workers' own resting places indicate a system where resources like food, including bread and fish, and care for illness were distributed with a sense of fairness. This provisioning was a brilliant social strategy, maintaining high morale and sustained productivity over decades of construction. The organizational model was further refined by leveraging seasonal rhythms. During the annual inundation of the Nile, when farming was impossible, a vast agricultural workforce became available for state projects. This cyclical influx of labor transformed a potential period of hardship into a productive national endeavor, providing sustenance and purpose to thousands. Overseeing this immense operation was a class of administrators and scribes. These were the ancient project managers responsible for quality control, scheduling, and recording the progress of each work gang. Their marks found on stones and in papyrus logs reveal a system of accountability that ensured every block met its exact specifications. But this was not a system driven by force alone. Communal rituals and festivals played a vital role in maintaining social cohesion. The entire project was punctuated by celebrations that honored milestones, much like the potlatch ceremonies of Pacific Northwest tribes, where communal feasting and gift-giving reinforced the bonds that held the society together. These events transformed labor from a duty into a shared, sacred mission. This raises a profound question about the nature of these ancient societies. Were these monuments built by coercion or by a collective agreement, a shared vision that united an entire culture in a common goal? The evidence of care for the workforce suggests a complex social contract, one where individual effort was recognized and rewarded within the grand design. This sophisticated human organization, this social engineering, prefigures the very principles of modern project management. It demonstrates an intuitive understanding that to build for eternity, you must first build a community capable of sustaining the dream. This intricate web of cooperation did not exist in isolation, but was part of a vast, interconnected world where these revolutionary ideas began to travel, carried along emerging routes of trade and cultural exchange. These monuments were never truly isolated. From the windswept plains of the British Isles to the high valleys of the Caucasus, a common architectural language of standing stones and burial chambers speaks of a world far more connected than we once believed. The appearance of similar megalithic structures across vast distances points not to independent invention, but to the slow, deliberate diffusion of ideas across ancient trade routes. This was a cross-cultural exchange of engineering knowledge, where core principles of stoneworking traveled with migrating artisans, were shared as diplomatic gifts, or were carried by pilgrims returning from distant lands. The result was a fascinating hybridization of techniques, as these shared ideas were adapted to suit local materials and spiritual beliefs. Experts point to the profound influence of Mesopotamian arch building, which, after passing through successive cultures, became a cornerstone of later Roman engineering. Similarly, the advanced quarrying skills developed in Egypt were likely transferred south to Nubia, where local builders then applied them to their own distinct architectural visions. The mechanisms of this exchange were as varied as the cultures themselves. Skilled stonemasons were sometimes sent as valuable assets in royal exchanges, their knowledge a form of living technology. Techniques were recorded on portable clay tablets or papyrus scrolls, creating a primitive but effective system for transferring complex information. More often, the process was one of slow assimilation, where a community would encounter a foreign style, understand its structural advantages, and then weave it into their own indigenous practices, creating something entirely new. A stunning case study of this blending is found in the rock-cut architecture of ancient India. After the campaigns of Alexander the Great, Hellenistic influences flowed eastward. Indian builders began carving elaborate facades and entire temples from cliff faces, but they integrated Greek proportions and decorative elements like scrollwork and pillars with their own rich symbolism of deities and mythological scenes. This was not mere copying, it was a creative fusion that gave birth to a unique and magnificent architectural style. This constant flow of knowledge acted as a powerful engine for innovation. One culture's solution to a problem could spark a revolution in another, thousands of miles away. Yet this diffusion also carried a potential cost. As techniques spread and were adapted, some of the original, highly specialized methods may have been lost or diluted over time, their precise nuances forgotten in favor of more practical, localized approaches. This interconnectedness reveals a profound truth about our ancient past. The greatest monuments were not the products of isolated genius, but of a shared, accumulating human intelligence. The movement of ideas across continents laid the groundwork for a universal understanding of form and force, principles that would eventually be codified into the very laws of physics we recognize today. The balanced rocking stones of India hold a silent lesson in physics. These massive boulders, poised so perfectly that a gentle push can set them in motion, yet so stable they resist the fury of monsoons, are monuments to an intuitive grasp of natural law. Ancient engineers possessed an empirical understanding of principles that science would only name millennia later. They knew that to move a great weight, you did not need overwhelming force, you needed a strategic point of leverage. The lever was their constant companion, from the simple logs used as rollers to the massive beams that pivoted obelisks into place. They understood center of gravity with an artist's touch, carving stones and designing foundations to distribute immense loads evenly, preventing the slow, destructive sinking that could doom a structure over centuries. Their entire approach was a masterclass in reducing effort. The inclined plane, in the form of an earthen ramp, was their most powerful tool, transforming the impossible vertical lift of a 70-ton block into a manageable, gradual ascent. This was an application of Newton's laws of motion in practice, long before the concept of inertia was formally defined. A body at rest, like a granite block on a sledge, remained at rest until a team of workers applied an external force. The momentum of that moving sledge then helped carry it forward, and for every action of the stone pressing down, there was an equal and opposite reaction from the compacted earth of the causeway supporting it. We can break down their genius into several core principles. First was the strategic distribution of load. By building pyramids with broad, massive bases, they ensured the weight of the upper layers was spread across a vast area, minimizing the pressure on any single point of the foundation. Second was the preference for trapezoidal shapes. From the narrowing profile of a ziggurat to the tapered doors of Mycenaean tombs, this form is inherently stable, resisting the lateral forces that can topple a sheer wall. Finally, they exhibited a deep knowledge of material properties. They knew that limestone possessed tremendous compressive strength, ideal for bearing the weight of the world, while harder stones like granite were reserved for details that required precision and durability. A profound example of this material science, though from a slightly later period, is the Roman discovery of concrete. By mixing lime with volcanic ash, they created a material that could cure underwater and withstand the ages. Yet the earliest monuments relied on pure mechanics, on a stone-on-stone intelligence that required no binder at all. Consider the generations of observation that led to these insights. A builder would notice how a stone settled differently on sand than on bedrock, or how a specific shape resisted toppling in high winds. This was a science born from relentless experimentation, a slow accumulation of wisdom through both triumph and catastrophic failure. Was this a lost science, a formal body of knowledge that has since vanished? It seems more likely it was a living, breathing tradition of problem-solving, an intelligence held in the hands and eyes of the artisans themselves. This profound, physical understanding of balance and force provided the invisible skeleton for every monument, a strength that then allowed for the expressive beauty that adorned their surfaces. The columns at Karnak are stories written in stone, their surfaces alive with gods and kings. This was not mere decoration applied after the engineering was finished. It was a fundamental layer of the design itself. The fluting carved vertically into each massive column did more than catch the light. It created an illusion of slenderness, making the stone appear to soar upward with a grace that a solid block could never achieve. This visual trick was a deliberate aesthetic choice that worked in concert with structural necessity, reducing the perceived bulk without sacrificing an ounce of the column's load-bearing strength. In many ancient traditions, ornamentation was a form of preservation. Detailed carvings and painted surfaces created a harder, more resilient skin that shielded the underlying stone from wind and rain, while the pigments themselves, often made from mineral oxides, acted as a protective sealant. The art was not just for show, it was a sophisticated form of weatherproofing that extended the life of the monument for centuries. We can see this philosophy in several brilliant subpoints. First, builders strategically placed intricate reliefs and friezes along the seams where large blocks met. These visual distractions drew the eye away from the necessary joints and cracks, creating a seamless visual narrative that made the structure appear to be carved from a single, miraculous piece of stone. Second, the use of color was a sophisticated code. Specific hues were used to signify different materials or structural functions, with a darker color perhaps indicating a load-bearing element and a lighter one a decorative panel, guiding the viewer's understanding of the building's logic even from a distance. Finally, artistic motifs were often aligned with celestial events. A carving of a sun god might be positioned so that a beam of light illuminates it only on the dawn of the summer solstice, weaving astronomical time directly into the architectural fabric. A stunning case study comes from the Byzantine era, where artisans set glittering mosaics directly into the curved surfaces of arches. The careful placement of each small tile within the mortar actually helped to lock the stones together more firmly, adding compressive strength and rigidity without contributing significant extra weight to the vulnerable arch. This harmony between form and function was essential to the spiritual experience. Walking through such a space was not just about seeing a building, it was about being enveloped in a living story, where every surface spoke of divine order and human devotion. Yet this integration sometimes required subtle compromises. A column carved with deep reliefs might be slightly thicker than a plain one to maintain its integrity, and painted surfaces required constant renewal by dedicated priests and artisans to prevent their protective magic from fading. This deep interconnection between art and engineering did not stop at the temple walls. It expanded outward to shape the very cities that grew around these monumental hearts. The grid of Mohenjo-Daro was a masterpiece of foresight. Its streets ran in perfect perpendicular lines, not for aesthetic appeal alone, but to channel water efficiently through a sophisticated underground drainage system, turning the entire city into a self-cleaning organism. This was urban planning as a form of social engineering, where the placement of every well, every bath, and every granary was calculated to sustain a vast, thriving community. The city's builders demonstrated a holistic vision, integrating their monumental architecture, like the Great Citadel and the large public bath, into a design that optimized space, security, and the very flow of daily life. Historians note how these early engineers employed a clear system of zoning. Residential districts with uniform brick houses were separated from industrial areas for crafts like beadmaking and pottery, preventing pollution and noise from disrupting the community. At the heart of it all stood the religious and administrative centers, built from durable stone and raised on massive platforms. These monuments served as immutable focal points, their permanence a visual anchor for the entire urban experiment. The planning elements reveal a deep understanding of the local environment. Major avenues were deliberately aligned to capture the prevailing winds, creating natural ventilation that cooled the densely packed streets during the intense heat. Vast, open plazas were strategically positioned at key intersections, providing spaces for public markets and communal gatherings, which reinforced social bonds and allowed for the exchange of goods and ideas. Even the defensive walls were multifunctional. They were not mere barriers, but broad, rammed earth terraces that offered residents elevated walkways with panoramic views and additional space for social interaction. This same principle of intentional placement is visible in the Acropolis models of ancient Greece. Temples like the Parthenon were not hidden away. they were positioned on the highest ground, visible from every corner of the city and the surrounding countryside. This was symbolic dominance in stone, a constant reminder of the city's divine patrons and the power of its rulers. It makes you wonder, did these comprehensive urban plans emerge from the decree of a single, powerful authority, or were they the product of a slower, communal consensus, a shared agreement on how a society should best live together? The evidence suggests that while a central vision likely guided the initial layout, its enduring success depended on a collective buy-in from the citizens who called these spaces home. This holistic approach to city building, where stone monuments were woven into the very fabric of daily existence, reveals that the greatest architectural achievements were those that served both the body and the spirit. The stones themselves, however, held a deeper language, a symbolic meaning that transformed a city from a mere collection of buildings into a map of the cosmos. The stones themselves were a permanent library, their surfaces etched with more than just stories of gods and kings. Deep within an Egyptian temple, the seemingly simple hieroglyphs adorning a pillar might secretly encode the mathematical ratio used to determine the ceiling's height, a clever way to preserve an architectural secret for eternity. This was a world where knowledge was too precious to be left on fragile papyrus, so they carved it into the very bones of their civilization. Structures became mnemonic devices, physical spaces designed to trigger memory. A priest walking a specific path through a temple courtyard, counting a precise number of steps between certain statues, could recall the entire sequence of a complex ceremony or the timing of an important celestial event. The number of steps in a pyramid might represent the days in a cosmological cycle, while the intricate geometric patterns in Islamic mosaics, repeating infinitely without beginning or end, were a visual representation of divine unity and the eternal nature of creation. Experts studying these sites suggest this was a deliberate strategy for cultural preservation. By embedding their core knowledge into architecture, they ensured it would survive wars, fires, and the slow decay of time, passing it securely from one generation to the next. This encoding took many brilliant forms. One method was the use of specific, sacred numbers repeated throughout a structure's design, each quantity symbolizing a different phase of the moon or a different realm of the cosmos. Another was the direct carving of star maps onto tomb ceilings, creating a permanent record of the night sky as it appeared on a significant date. Perhaps most intimately, oral histories and founding myths were woven into vast stone reliefs, turning a wall into a storybook that could be read by anyone who understood the symbolic language. A profound case study exists in the Nazca lines of Peru. These enormous geoglyphs etched into the desert floor may have served as ceremonial walking paths. As participants moved along the lines of a giant spider or a hummingbird, they were not just performing a ritual, they were physically tracing paths that were also maps, embedding crucial knowledge about water sources, seasonal changes, and sacred ancestral routes directly into the landscape through collective memory. This layering of meaning makes us wonder, were these intricate codes intended for everyone or only for a select group of initiated priests and scholars? The answer likely lies in between, with different levels of meaning accessible to different members of society. For the general public, the grand carvings told a story of power and divine favor, while for the educated elite, the same walls held the blueprints of their science and philosophy. This practice transforms our understanding of these monuments from silent ruins into living repositories of a lost world's intellect, and it inevitably leads us to ponder the individuals, the master artisans and visionary engineers whose hands and minds gave form to this eternal stone language. Hidden within the stones of European cathedrals are faint, personal marks, the signatures of the anonymous masons who carved them, These symbols were more than just a claim of work. They were part of a complex language of apprenticeship and guild knowledge, a system designed to protect hard-won expertise. This was a world where the individual artisan held the key to monumental achievement, their specialized skills passed down through years of hands-on training. A master planner, the visionary behind an entire project, directed the work, but it was the countless artisans who perfected the joinery and carving that gave these structures their soul. Epigraphic evidence, the study of ancient inscriptions, reveals that in many societies these builders held remarkably high status. Their methods were guarded trade secrets, a form of intellectual property that was as valuable as the stone itself. The training process was a long and rigorous journey. A young apprentice would spend years simply observing, fetching tools, and mixing mortars before ever being allowed to touch a chisel to fine stone. This slow, immersive education was not just about learning technique. It was about absorbing a philosophy of work, a deep respect for the material, and an understanding of its hidden strengths. Within this system, individual craftsmen were constant innovators. A quarryman might devise a new way to angle his wedges for a cleaner fracture, or a sculptor might perfect a new type of drill bit that allowed for more delicate features. This spirit of invention was balanced with a profound reverence for tradition, creating a dynamic where each generation could build upon the wisdom of the last without discarding proven methods. Collaboration was essential, a constant dialogue between different trades. The quarrymen who understood the stone's raw character had to communicate with the sculptors who would reveal its final form, and both answered to the master masons who ensured every piece fit the grand design. A powerful example is Imhotep in Egypt, the brilliant architect credited with designing the first pyramid. His wisdom was so revered that he was later deified, a rare honor that speaks to the immense respect afforded to master builders. Yet for every Imhotep, there were thousands of skilled hands whose names are lost to time. Were their identities intentionally suppressed by the collective nature of these projects, or was their personal glory found in the enduring legacy of the work itself? The subtle chisel marks they left behind suggest a quiet pride, a desire to be remembered by the stone, if not by history. Recognizing the agency of these individuals, their creativity, and their specialized knowledge naturally leads us to wonder about the world that made their work possible, the sophisticated economic systems that mobilized and sustained such vast, skilled labor forces. The stones for a pyramid began not in a quarry but in a ledger. Monumental architecture was at its heart, a colossal economic enterprise, fueled by intricate trade networks that spanned continents. To face a temple in gleaming white marble or to equip workers with razor-sharp obsidian tools required more than just skilled hands. It demanded sophisticated diplomacy and the ability to pool resources across entire regions. This was the hidden economy of the sacred, a system where the divine vision of a pharaoh or priest was made possible by the pragmatic management of goods, labor, and time. Experts studying these projects note that many were deliberately phased over generations, allowing communities to accumulate wealth slowly and adapt their plans to changing political or environmental conditions, turning a single lifetime's ambition into a multi-generational legacy. The economic engine can be broken down into several key components. First was the barter and management of skilled labor. Artisans who carved hieroglyphs or fitted interlocking stones were often compensated with goods like grain, oil, and housing, their specialized knowledge making them a valuable, protected class. Second was the colossal undertaking of supplying food and water for thousands of workers, a logistical feat that required the collection and redistribution of agricultural surplus, often functioning as an early form of taxation. Finally, there was the strategic investment in infrastructure. Building a causeway to transport stones was not just a construction expense, It was a long-term economic asset that facilitated trade and communication long after the monument was complete. A clear case study emerges from the Roman Empire, where conquest provided vast wealth and access to large groups of laborers. Yet, for most earlier societies, the evidence points to a system built far more on social cohesion and voluntary participation, where contributing to a communal temple was a civic and spiritual duty. This raises a profound question about the social cost of these wonders. Did these economic strategies foster a more equitable society by providing sustenance and purpose, or did they inevitably lead to the hardship of some for the glory of a few? The answer is complex, woven into the fabric of each unique culture. Some projects seem to have functioned as a form of ancient public works, redistributing resources during seasons when farming was impossible, and uniting a population around a shared identity. This economic lens reveals that the true foundation of these timeless monuments was not just stone and mortar, but a deeply pragmatic understanding of human collaboration and resource management on a staggering scale. Teams of modern builders strain against ropes, their muscles burning as they attempt to move a 20-ton block of limestone using nothing but wooden sledges and a path of wet clay. This is not a scene from a film, but the rigorous practice of experimental archaeology, a field dedicated to testing the hidden engineering of the past through hands-on replication. When researchers tried to transport a Stonehenge-sized monolith, they confirmed a long-held theory, discovering that a crew of around 150 people could move the massive stone on a lubricated track with surprising ease, its friction coefficient far lower than anyone had assumed. This empirical approach bridges millennia, turning hypotheses about ancient methods into tangible, physical truth. The process often begins with building precise scale models to understand the physics of a proposed technique, like using a lever and counterweight system to raise a massive obelisk. Advanced tools like three-dimensional scanning allow scientists to analyze ancient tool marks with microscopic detail, comparing them to marks made by reconstructed tools to identify the exact methods used. In one landmark experiment, a team succeeded in erecting a small obelisk using a pivoting technique and a giant sandbox, demonstrating how controlled drainage could lower the stone's base with perfect control. Another study focused on the acoustic properties of ancient spaces, building simulated chambers to measure how specific resonant frequencies could be intentionally engineered into the design. The analysis often extends into the digital realm, where computer modeling stress tests ancient designs against earthquakes and heavy loads, revealing why certain shapes, like the trapezoidal doors in Mycenaean tombs, possess such inherent stability. Perhaps the most illuminating experiments involve the ongoing efforts to replicate the perfect stone fitting of the Inca. Teams of stonemasons using only stone hammers and abrasive sand have demonstrated that the method was likely a patient combination of pounding the surfaces to a rough shape followed by meticulous grinding, a process that could take many months for a single block. These reconstructions consistently reveal unexpected efficiencies that challenge our modern assumptions about technological progress. They suggest that the ingenuity of early societies was not measured in horsepower or engine capacity, but in a profound understanding of leverage, friction, and human coordination. This empirical dialogue with the past does more than just solve old puzzles. It offers a quiet lesson for our own time about the power of simplicity and the deep intelligence embedded in hands-on craftsmanship. The ancient world holds a blueprint for our future. Today's most innovative architects are looking back, not forward, for solutions to our modern environmental challenges, finding profound wisdom in the very stones of our earliest monuments. This is not about replicating the past, but about rediscovering a forgotten intelligence, a way of building that worked in concert with the earth rather than conquering it. The principle of thermal mass, for instance, was mastered thousands of years ago. The thick stone walls of ancient structures act like a natural battery, absorbing heat during the day and slowly releasing it at night, creating a stable, comfortable indoor climate without any need for mechanical systems. This passive temperature regulation is a cornerstone of modern sustainable design, a direct echo of techniques used in everything from Roman villas to the cliff dwellings of Mesa Verde. Experts point to the brilliant wind catchers of traditional Persian architecture, tall towers that capture cool breezes and funnel them down into buildings, creating a natural and energy-free form of air conditioning that puts our power-hungry systems to shame. We can break down these applicable ideas into several powerful strategies. The first is the use of local and natural materials, drastically reducing the carbon footprint associated with transporting modern building supplies over vast distances. The second is the adoption of ancient seismic adaptations, like the flexible foundations and interlocking stonework that allowed Inca walls to dance with earthquakes, principles now being studied for building resilient cities in fault zones. The third is the revival of geometric proportions, not just for beauty, but for the documented sense of well-being and harmony they create for inhabitants. A stunning case study can be found in modern eco-villages that use rammed earth techniques, compressing local soil into incredibly durable and well-insulating walls, a method directly derived from the construction of the Great Wall of China and other ancient fortifications. Even the concept of integrating green spaces, reminiscent of the legendary Hanging Gardens of Babylon, is being reimagined as living walls and rooftop gardens that cool urban heat islands and promote biodiversity. These time-tested methods offer more than just nostalgia. They provide a viable path forward. They challenge our obsession with complex technology and remind us that some of the most elegant solutions are found in a deep understanding of the local environment, the sun's path, and the wind's direction. The true legacy of these ancient engineers may not just be the monuments they left behind, but the sustainable blueprint they offer for a world in urgent need of balance. This enduring relevance forces us to confront a deeper question about the very nature of innovation itself. The idea that ancient wonders required otherworldly help is a story that refuses to fade. We often hear that the pyramids were built by visitors from the stars, a theory that dismisses the mountains of evidence left by the very human hands that shaped them. This persistent myth, while captivating, overlooks the profound truth of our own ancestors' capabilities. Historians point out that while certain details of their methods are still being uncovered, there is no gap in the archaeological record so vast that it requires an extraterrestrial explanation. Human creativity, honed over generations of trial and error, is more than sufficient to account for these marvels. Take the claim that stones were levitated with sound. This notion crumbles under simple logic. The precise tool marks found on Egyptian granite, for instance, perfectly match the grooves left by experimental archaeologists using copper saws and an abrasive slurry of wet sand. These are the tangible fingerprints of human labor, not the residue of a mysterious technology. Another popular myth revolves around a lost super-civilization, an advanced society that vanished without a trace. Yet the story of engineering is not one of disappearance, but of clear and continuous evolution. We can trace the development of quarrying techniques from the rough stone hammers at Göbekli Tepe to the organized production lines at Giza, a lineage of innovation spanning thousands of years. Even the incredible astronomical alignments are misrepresented as proof of alien contact. In reality, these alignments demonstrate a deep, patient, and brilliant observation of the natural world, a human achievement that connects the Earth to the cosmos. Why do these alternative theories hold such power? They often emerge from a place of awe, a sense that our modern world could not replicate such feats. Yet this perspective inadvertently diminishes the true wonder, the reality of communities working in unison, of brilliant minds solving immense problems with the tools they had. It shifts credit away from the countless artisans and engineers whose ingenuity literally moved mountains. By critically examining these claims, we do not lose a sense of mystery. Instead, we gain a deeper appreciation for the real, tangible, and profoundly human story of perseverance and collective genius that stands behind every stone. This clearer view allows us to finally gather the most vital lessons from this entire journey through time. The silent stones of Machu Picchu are under a new kind of siege. Not from conquistadors, but from the relentless footsteps of millions and the shifting patterns of a changing climate. Preserving this legacy is an urgent engineering challenge in its own right, one that demands we learn from the very builders we seek to honor. Modern conservationists are now turning to the original Inca wisdom, reinforcing the ancient agricultural terraces with the same interlocking stone techniques that have held them firm for centuries, and clearing the sophisticated drainage channels the Inca designed to prevent water from undermining their city. This is more than simple repair. It is a dialogue with the past, an effort to protect these sites not as frozen relics but as living repositories of human knowledge and cultural heritage. Experts monitoring these locations warn that climate change, with its intensifying rains and prolonged droughts, accelerates erosion in ways the original engineers could never have anticipated, while unchecked human activity physically wears away the stone. The challenge is a delicate balancing act, providing access for the world to witness these wonders while simultaneously shielding them from the damage that very attention can cause. To achieve this, conservators employ non-invasive surveys like LiDAR, using laser pulses from aircraft to map the ground beneath the jungle canopy and monitor structural health without ever touching a fragile wall. The most successful strategies actively involve local communities in the ongoing maintenance, blending their ancestral connection to the land with modern scientific tools. A profound and poignant case study is found in the Bamiyan Valley of Afghanistan, where teams are meticulously documenting every remaining fragment of the giant Buddha statues lost to conflict. This painstaking work, a form of digital preservation, keeps open the possibility for future restoration, honoring the vision of the original artisans even in the face of loss. It makes you wonder, what do we truly lose when a site like this is neglected or destroyed? We forfeit a unique chapter in the story of human innovation, a physical key to understanding how our ancestors saw their world and their place in the cosmos. These preservation efforts are a testament to the enduring impact of ancient engineering, a recognition that these stones still have vital lessons to teach us, but only if we are wise enough to protect them. Ground-penetrating radar now reveals voids within the Great Pyramid that no modern eye has ever seen. For all we have learned, the stones still guard their deepest secrets. The most profound mysteries are not just about how they built, but why certain features exist at all. Consider the massive stone spheres of Costa Rica, perfectly rounded monuments whose purpose remains a complete enigma. Were they territorial markers, astronomical tools, or symbols of cosmic belief? We simply do not know. Similarly, the sprawling alignments of thousands of stones at Karnak in France stretch for miles across the landscape. The leading theory suggests this was a complex astronomical calculator, a stone computer for predicting celestial events, yet its true function is still debated by researchers. These are not minor gaps, but vast canyons in our understanding. New technologies are providing fresh paths to answers. scientists are now performing DNA analysis on the organic materials trapped in ancient mortar, hoping to trace the geographic origins of the materials and map the trade routes that supplied these massive projects. Virtual reality allows archaeologists to run construction simulations, testing different theories of ramp design and labor organization in a digital sandbox to see which methods are most feasible. There are also tantalizing hopes for a textual discovery. What if a library of engineering manuals written on perishable papyrus or clay tablets lies hidden in an undiscovered tomb? Such a find would revolutionize our knowledge. Another pressing question involves the role of women in these monumental endeavors. While often invisible in traditional narratives, forensic analysis of worker cemeteries is beginning to suggest that women were present at construction sites, perhaps in roles of management, craft specialization, or ritual observance. The story is far more complex than we once assumed. These unanswered questions are not a sign of failure, but a beacon for the future. They remind us that the past is not a closed book, but a living field of inquiry. Every mystery solved seems to reveal two more, inviting us to look deeper and listen more closely to the whispers from the stone. The true legacy of these ancient structures is written not in myth, but in the enduring language of stone and sky. Our journey through the hidden engineering of our ancestors reveals a profound truth. Their mastery of materials, physics, and human collaboration rivals the expertise of our modern world. From the interlocking stonework of the Inca that dances with earthquakes to the celestial alignments of the Egyptian pyramids that map the heavens, we see a global legacy of innovation. This intelligence was not born from advanced technology, but from deep observation, generational patience, and a cultural drive to infuse meaning into every block and joint. These monuments are far more than simple piles of rock. They are testaments to the boundless creativity of the human spirit, urging us to look past fantastical stories and appreciate the tangible, breathtaking achievements of ancient societies. The next time you see an image of these wonders or are fortunate enough to walk among them, I hope you see them with new eyes, notice the seamless joints, consider the journey of the stone, and feel the echo of the communal effort that brought it to life. I would love to hear which method amazed you the most, perhaps the ingenious transport systems or the celestial precision, so share your thoughts in the comments below. If you enjoyed this deep dive into history's great mysteries, subscribing will bring you more explorations into our shared past. Let us carry forward the ultimate lesson from these master builders, that with shared purpose and relentless ingenuity, even the simplest tools can create wonders that stand for millennia.